Hello, welcome to a video on section 3.8 regarding the derivatives of inverse trig functions. So we're going to start by finding the derivative of inverse sine x. Now remember that if y equals inverse sine x, then that would imply that x equals sine y, because that's how we would isolate y in the first place. If x equals sine y, it could be isolated by saying y equals inverse sine of x. Also, you may remember our default range for inverse sine, which is from negative pi over 2 to pi over 2. That's so that we can guarantee that the inverse function is actually a function. So if I took the derivative of both sides with respect to x, then of course that becomes 1 on the left side. The other side, we're using implicit differentiation, you get cosine y, but times dy over dx. So dy over dx is 1 over cosine y. So in essence, the derivative of inverse sine of x is 1 over cosine y. But it's still a little weird because we want our derivative in terms of x. So if we take a look at the Pythagorean identity, and if I isolate cosine y, I should get this. Square root both sides. So cosine y is plus or minus root 1 minus sine squared y. Now, given the fact the way our inverse sine graph looks, inverse sine graph is right over here. The tangent lines will have positive slopes. So if tangent lines have positive slopes here, in that entire range, from negative pi over 2 to pi over 2, then we're probably just going to want to go with the positive square roots. And since x equaled sine y, we could safely say that's the same thing as root 1 minus x squared. So the derivative of inverse sine, instead of 1 over cosine squared y, instead of 1 over cosine y, we can write as 1 over root 1 minus x squared. Now this is a must to know. So we'll take it, you'll want to memorize it, but that's how you can actually derive it, by just thinking of what inverse functions do. Y equals inverse sine of x, well x equals sine y. Take it to both sides using implicit differentiation. Then using a little bit of nifty trig stuff that we know. Cosine squared, sine squared plus cosine squared is 1. Isolate cosine y, and then substitute back in, we should be okay. And again, our default range is going to be from negative pi over 2 to pi over 2, mainly because we want the inverse sine to be a function itself. Also because, remember, for y equals sine x, sine can never be larger than 1, and sine can never be less than negative 1. And we kind of can keep that contained when our range for inverse sine is from negative pi over 2 to pi over 2. Or more generally, if you have an inverse sine of u, where u is some function in terms of x, we can write as 1 over root 1 minus u squared times the derivative of u with respect to x. For example, say I had to find the derivative of the inverse sine of 7x plus x squared. Then it's 1 over root 1 minus, the inside. Squared times the root of the inside, 7 plus 2x. Coming back here again, our domain is between -1 and 1. Or you can write interval notation like that. Mainly because we can't divide by 0 and we can't square root negative numbers. So another thing to keep in mind that there is a specified domain for the derivative of inverse sine. Okay, now that will conclude page 1 of the notes. Let's look at page 2 of the section 3.8 notes. So if y equals tan x, then of course x equals inverse tan of y. Now, we do a similar default range from negative pi over 2 to pi over 2, but non-inclusive. That's a default range for inverse tan. If I use implicit differentiation, so if I take the derivative with respect to x, that'll be 1 equals actually, sorry about that, so we'll see x equals tan y. X equals, and actually, what am I doing here? Y equals tan x, so x equals inverse tan of y. Or, I guess if we had x equals tan y, y is inverse tan of x. Sorry about that, that was a really big goof. So, x equals tan y, take derivative with respect to x, get 1 equals secant squared y times dy over dx, or dy over dx equals 1 over secant squared y. Okay. So now if I use one of my trig identities, 1 plus tan squared y equals secant squared y, we can think of it as 1 plus x squared, because x equals tan y, right? Equals secant squared y. So the derivative, instead of 1 over secant squared y, can be re-expressed as 1 plus x squared. And if we had some function u in terms of x, so you have inverse tan of u, or u could be some other function besides plain old x, you can write as 1 over 1 plus u squared times d over dx. So again, to recap, and I apologize for messing that up, what if we had x equals tan y, then to get y equals inverse tan of x, and then if y equals inverse tan of x, again, same thing, saying x equals tan y, default range negative pi over 2, pi over 2, take derivative with respect to x of x equals tan y. We do get, and gotta use implicit differentiation, 1 equals secant squared y times dy over dx, get dy over dx by itself. And then using our trig identities right here, and also realizing x equals tan y, we can substitute, and we get the derivative of inverse tan x. The domain of that function is actually all real numbers, or negative infinity to infinity. You can plug in whatever you want to 1 over 1 plus x squared. And we see that the slope's always going to be positive if you drew tangent lines. So the tangent lines are all positive. Not going to quite go through the whole derivation for secant or inverse secant, but it'll be this. Or if you had some function u in terms of x, 1 over absolute value of u times square root of u squared minus 1 times derivative of u with respect to x. And the domain for that actually is from negative infinity to 1 and from 1 to infinity. We can't plug in 1 because then you have 0 on the bottom. So you want to be careful about that. And the graph of inverse secant x is right there, which you may have done in pre-calculus, hopefully. If not, that's how it looks. And we see that slope scan is always positive. So we kind of maintain that. And then lastly, for the last 3 inverse trig functions, they're right here. Now, you might remember these identities, the cofunction identities. Inverse sine plus inverse cosine equals pi over 2. Inverse tan plus inverse cotangent equals pi over 2. Inverse secant plus inverse cosecant equals pi over 2. And then you can kind of do a little bit of a rearranging where you isolate inverse cosine, isolate inverse cotangent, isolate inverse cosecant. And these we already found. We already found these derivatives. And by the way, when you talk about cofunctions, in some ways, they're complements of each other. Like sine alpha, I know is 3/5 here. Cosine beta, well, is also 3/5. Alpha plus beta, of course, is 90 degrees. So alpha is the inverse sine of 3/5. Beta is inverse cosine of 3/5. And those have to equal 90 degrees. So I hope that gives you a better understanding why inverse sine plus inverse cosine is equal 90 degrees. Because the sine of, like, say, 40 degrees equals the cosine of 50 degrees. So the sine of an angle equals the cosine of its complement. Likewise, the tan, cotan, secant, cosecant. Now, if I took the derivative of this, of both with respect to x, I'm going to have 0 minus the derivative of inverse sine, which I know is 1 over root 1 plus x squared. If I take the derivative of that right there, derivative of pi over 2 is 0, derivative of inverse sine is 1 over 1 plus x squared. So it's really just negative 1 over root 1 plus x squared. Derivative of inverse cosecant, negative 1 over 1 plus x squared. Derivative of inverse cosecant, negative 1. So it's the same thing as secant, tangent, and sine. You just do the negative counterparts. Or just do negative for the counterparts. Now let's look at examples 1, 2, and 3. And after that, I will stop the video. So given y equals x times inverse cosecant of x, of course, product rule. So derivative of x is 1 plus x times negative 1 over root 1 plus x squared. Or you can kind of clean it up, make it look like that. Arctan, if you forget, it's the same thing as inverse tan. And that's going to be t to the 1/2 power. So if I take, and actually that's y prime for example 1, sorry about that. So s prime will be 1 over 1 plus x squared, or in this case 1 over 1 plus t1 half raised to the second power, times the derivative of the inside, 1 half times t to the negative half. So it's 1 over 1 plus t times 1 over 2 root t. And then we have to validate this at t equals 9. So it's 1/10 times 1/6, where you get 1/60th in that regard. Lastly, is find equation for a normal to the graph. Okay, so remember y minus y1, m times x minus x1, but we will need to do the negative reciprocal slope because the derivative is the slope of the tangent line, but we want the normal, so it's perpendicular. So how does that one work out? Y prime will be -1 over root 1 plus x over 4 squared times we have x over 4, which is 1/4. Clean up just a little tad, -1 over 4 root 1 plus x squared over 16. Now, at this point I can now plug in 2. So it's -1 over 4 root 1 plus 1/4. If you plug in 2, you get 2 squares 4. 4 over 16 is 1/4. Oh, oops, that should be a minus. 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 So slope is kind of crazy here, but it's going to be -1 over root 3/4. And still we have the 4 there. -1 over 4 times root 3 over 2. -1 over 2 root 3. So the perpendicular slope, of course, is 2 root 3. So y minus something equals 2 root 3 x minus 2. And looking at the original equation, do a little contrast, do red. If you plug in 2 into that, inverse cos of half, that will be pi over 3. And that's how I get pi over 3 over here. So that concludes the first 3 pages of the section 3.8 notes.